Hi, my name is Alex Gurwich. I'm an NSF graduate fellow at Northwestern University. And in this recording, I'm going to tell you a little bit about feedback-regulated star formation in galaxies that evolve from bursty clumps to time-steady disks. Now, spiral galaxies are relatively rare in the high redshift universe. If you look at redshifts above 0.5, you're more likely to find a galaxy that's a clumpy spheroid than you are to find a grand design spiral like we're used to seeing in the local universe in beautiful images that come from the Hubble Space Telescope. Really what I mean to say is that galaxies will transition from dispersion-dominated spheroids to rotation-dominated disks as they increase in mass over time, in a phenomenon that's termed disk settling. Now, disks will settle theoretically too in the fire simulations. The fire simulations are a suite of high-resolution cosmological hydrodynamic zoom-in simulations. What that means is that they're a simulation of an individual galaxy while also including its cosmological environment. So things like accretion from the IGM, satellite galaxies, self-consistently formed CGM, all while being high resolution enough to resolve individual star-forming regions. When you put all of that together, what you end up with are these beautiful spiral disk galaxies that will form and emerge naturally in the simulation volume, having evolved from clumpier, more spheroidal, more explosive progenitors. So that's quantified here. In the left panel, I'm plotting something I'm calling the diskiness, which is really the ratio of the angular momentum in the z direction to the total angular momentum. What I want you to notice is that at early times, the diskiness is relatively low and very time variable. Whereas at late times, it's really nailed itself to a value close to 1, meaning that all of the angular momentum is concentrated along the z-axis, rotating. Likewise, if you look at the star formation rate, at early times, it's much more time variable or bursty, whereas at late times, it's really nailed itself down to a more time-steady rate. Now, because of the time limitations of this recording, we're only going to be able to talk about the disks after they've formed and are relatively stable. So this is one of those disks, looking edge on. What I want to draw your attention to is the very complicated phase structure that we can see in the top panel. So those bright blue clumps are going to be the cold, dense, bound gas, whereas the hazy green stuff is the more hot, diffuse gas. And really what I see when I look at this are these pockets of hot gas mixed in with the warm envelopes that surround the very cold, dense cores. And so when we look at something like this and we say that it's time steady, I think it begs the question of whether something like this is in a state of hydrostatic equilibrium. So hydrostatic equilibrium is an assumption that's often made in models of galactic disks. So it's a question that's worth asking for its own sake. But it's also the basic assumption for a set of star formation models, termed equilibrium star formation models, where they balance the pressure and the weight to connect the star formation rate surface density to the gas surface density. And in so doing, derive the observed Kennecott-Schmidt relation. So what you should have in your mind is that the gas wants to collapse toward the midpoint. And in doing so, it compresses, triggering star formation. Those young stars will return energy to their environments through stellar feedback, driving turbulence and creating a pressure that will push back against the weight of the gas. When these two balance, you'll get a steady state, static solution with a single star formation rate. And now the scaling between the gas surface density and the star formation rate surface density not only matches the Kennecott-Schmidt relation, but also has the right normalization, which makes this class of models very attractive. But before I continue, I want to try and introduce something that's a little bit different from this picture. So here we're starting with the equation of hydrostatic balance. So hydrostatic balance is just when the weight is equal to the gradient of the pressure, and the pressure includes terms like a thermal pressure or maybe even a turbulent pressure, depending on the system that you're looking at. I want to contrast that with a more general state of dynamical equilibrium, which comes from the Euler equation, that contains this convective term. And so what this is really saying is that you can consider it as another pressure, something like a kinetic energy density associated with a bulk flow moving coherently, whereas in hydrostatic equilibrium, there's no such thing. So having defined that concept, I want to bring up two main questions that we tried to address in a paper that we published last year. There's only a small subset of the things that we put into the paper, so if you're interested, please go check it out. So number one, are those basic model assumptions, those two equations I flashed earlier, actually satisfied in the fire simulations? And two, where there are deviations from that equilibrium, are they connected to dispersion in the KS relation? And so first I want to say that the first basic assumption is, are the galaxies in hydrostatic equilibrium? The answer is no, they're not. So if you look just above the midplane, hot gas is being launched at a relatively high velocity. That hot gas will continue to larger heights until its velocity eventually changes sign and it merges with the coherent inflow moving in. But if we consider instead whether the gas is in a state of dynamical equilibrium, then the answer to our question changes. If we compare the total midplane pressure, including the bulk flow and thermal pressures, to the weight of the overlying gas, what we find is that the pressure does balance the weight. Likewise, if we compare the total pressure, including these two new terms, to the star formation rate surface density, we find that the two are proportional. And so we're still able to rederive the Kennecott-Schmidt relation by connecting the star formation rate surface density to the gas surface density through these two equations. But looking in that last plot, not everything lied along the P equals W line. So we want to understand if there are deviations from equilibrium, what do they mean? And so if we plot the pressure to weight ratio over a face-on map of the galaxy, we can start to see that indeed there really are pretty large deviations in some regions of the galaxy, sometimes up to a factor of 10 in either direction. This is especially obvious as you look on smaller and smaller averaging scales, like we see in the bottom right panel. So if you end up taking a radial annulus and you compute something like the standard deviation of the pressure to weight ratio as a function of radius, what you'll see is that there's a systematic increase in the scatter in the pressure to weight ratio as you look on smaller and smaller scales. Now this hopefully reminds you of something in the observed Kennecott-Schmidt relation, that there's a similar observation of increasing scatter as you look on smaller and smaller length scales. So if we compare the scatter in the 2 kpc observations, which is something like half a dex, to the scatter that we measure in our simulations in the pressure to weight ratio, find that it's also something like half a dex. Likewise, if you compare the scatter in the observations at 500 parsecs, it matches pretty well with the scatter in the pressure to weight ratio in the 100 to 300 parsec range. And now I want to emphasize, I'm not trying to draw a one-to-one comparison between the scatter in the pressure to weight ratio and map it to scatter in the observed Kennecott-Schmidt relation, because of course there's going to be all sorts of sources of observational uncertainty in the KS relation. But rather, I want to point out that the scatter in the pressure to weight ratio should represent a minimum theoretical uncertainty in the KS relation that comes from the ISM's inability to regulate to a state of dynamical equilibrium, and that this minimum seems to be a large part of the scatter. And so bringing these questions back, number one, are the basic model assumptions satisfied in the fire simulations? I would say yeah, not quite in the way that we originally expected, but there is dynamical, not hydrostatic equilibrium. Number two, where there are deviations, are they connected to the dispersion in the KS relation? And yeah, scatter in the KS relation seems to be related to scatter in the pressure to weight ratio, which makes sense because it should be a theoretical minimum scatter just based off of the ISM's ability to regulate itself. So since publishing this paper last year, we've been starting to address some still unanswered questions that I haven't had enough time to talk about here. And so, like I said earlier, we've only really looked at the low redshift versions of these galaxies. At high redshift, we want to understand if there could still even be dynamical equilibrium during the bursty phase, or what might break down, at the higher redshifts. As well, it's been found in our simulations that the end of bursty star formation coincides with the emergence of a hot halo in the CGM. So we'd like to understand the relationship between the hot halo and the formation of a galactic disk. So with that, I'm out of time. I'll flash up my questions and I'll thank you for watching this recording.